Picture this. Somewhere out there in the cosmic darkness, there's an object so massive, so incomprehensibly large, that it could swallow 11 entire solar systems side by side. Not 11 planets, 11 complete solar systems. Everything from the sun to the furthest reaches where comets drift in the Oort cloud, multiplied by 11, and it all fits comfortably inside this single entity. Now here's the wild part. This isn't science fiction. This thing actually exists, and it's called a black hole. But what makes black holes truly mind-bending isn't just their current size. It's the fact that unlike every other object in the universe, they have absolutely no physical size limit whatsoever. Planets, they can only grow so big before their own gravity tears them apart. Stars, same deal. Even the most massive stars we know have a ceiling they can't break through, but black holes, they can literally grow forever. Give them enough matter and enough time, and there's theoretically no upper boundary to how enormous they can become. Think about that for a second. In a universe filled with limits and boundaries, these cosmic monsters are the only things that can break free from those constraints entirely. Which raises a fascinating question. If black holes can grow infinitely large, just how big is the biggest one we've actually found? And more importantly, how did something that massive even come into existence? Let's begin. Part 1. Introduction and primordial black holes. From atoms to mountains, understanding primordial black holes. Before we hunt down the largest objects in the universe, we need to start at the complete opposite end of the spectrum. We're talking about black holes so small they make a grain of sand look like a boulder. These are called primordial black holes, and they might be the oldest objects in existence, older than atoms themselves, older than the first stars, possibly even older than light. Here's where things get really interesting. Right after the Big Bang, the universe wasn't the relatively calm place we see today. It was an unimaginably dense, violent soup of pure energy. Everything was packed together so tightly that even the tiniest irregularity in density could have catastrophic consequences. Imagine a concert where everyone's shoulder to shoulder, and someone in the middle of the crowd suddenly takes up just a little more space than everyone else. In a normal concert, people just shift around. But in the early universe, that tiny difference in density could trigger a runaway collapse. These pockets of slightly denser material would have been crushed by their own gravity into infinitesimally small points, primordial black holes. And we're not talking about your average black hole here. These things would be mind-bogglingly tiny. The smallest primordial black hole that could theoretically still exist today would weigh about 1 trillion kilograms. Now, 1 trillion kilograms sounds massive, right? That's roughly the mass of a large mountain. But here's the kicker. This mountain's worth of mass would be compressed into something no bigger than a proton. A proton, that's about 1/10,000,000th of a millimeter across. Let's put that in perspective. If you had a primordial black hole with the mass of the entire Earth, all 6 sextillion kilograms of rock, iron, water, and air compressed down, it would barely be larger than a coin you carry in your pocket. The entire planet Earth crushed into something you could theoretically flip like a quarter. That's the level of density we're dealing with here. The dark matter connection nobody expected. Now here's where primordial black holes go from merely fascinating to potentially universe-changing. We haven't actually observed any of these tiny black holes yet. They're incredibly difficult to detect because they're so small and they don't emit light. But some scientists think they might have found evidence of their existence in the most unexpected way possible. You've probably heard about dark matter. That mysterious, invisible stuff that makes up about 85% of all matter in the universe. We know it's there because we can see its gravitational effects. Galaxies spin too fast to hold together based on the visible matter alone. Something invisible is providing extra gravitational glue, keeping everything from flying apart into the cosmic void. For decades, physicists have been scratching their heads, trying to figure out what dark matter actually is. Exotic particles, strange quantum fields, dimensions we can't perceive. But what if the answer is simpler than we thought? What if dark matter isn't some exotic new particle at all? What if it's just countless trillions of these primordial black holes, scattered throughout the universe like cosmic dust, invisible but gravitationally powerful? It's a controversial idea, and we don't have definitive proof yet. But think about the elegance of it. The invisible glue holding galaxies together might be the universe's oldest black holes, born in the first fraction of a second after the Big Bang. Here's what makes this theory so compelling. Primordial black holes would be almost impossible to detect individually because they're so small, but collectively, their combined gravity would be enormous. They'd create exactly the kind of gravitational effects we attribute to dark matter. And unlike exotic particles that might or might not exist, we know black holes are real. We've seen them, measured them, photographed their shadows against the cosmos. Could the universe's greatest mystery be solved by its smallest black holes? We don't know yet, but the possibility is tantalizing. When reality surpasses theory, let's step back and appreciate how strange this whole situation is. For most of human history, black holes were pure mathematics. Einstein's equations predicted them, but Einstein himself didn't believe they could actually exist in nature. They were too extreme, too bizarre. A point of infinite density where the laws of physics break down. Come on, that's the stuff of theoretical daydreams, not reality. Yet here we are, discussing different types of black holes, like we're comparing species of animals. Not only do black holes exist, but they come in an incredible variety of sizes, from smaller than an atom to larger than our entire solar system. And unlike animals, which evolved over millions of years, or stars, which form over millions more, some of these black holes could have appeared in the literal blink of an eye. Cosmically speaking, the primordial black holes we've been discussing would have formed in less than 1/1,000,000th of a second after the Big Bang. No gradual process, no slow collapse, just instant creation of objects so dense that nothing, not even light itself, can escape their gravitational pull once it crosses a certain boundary. And these instantaneous monsters might still be out there, drifting through space, invisible architects of galactic structure. But here's what really gets me. We're living in a unique moment in cosmic history. Right now, today, we have the technology to potentially detect these ancient objects for the first time ever. Gravitational wave detectors are getting more sensitive. Space telescopes are pushing deeper into the universe. Particle accelerators are probing the fundamental forces of nature. We might be on the verge of confirming that primordial black holes exist, or ruling them out entirely. Either way, we're about to learn something profound about the universe's first moments, the scale of the invisible universe. Before we move on to the black holes we know for certain exist, let's really internalize what we're dealing with here in terms of scale. Because the numbers involved are so extreme that they almost lose meaning. Our brains aren't wired to comprehend these kinds of values intuitively. 1,000,000,000,000 kilograms compressed into a proton-sized space. What does that even mean practically? Well, if you could somehow hold one of these primordial black holes in your hand, which you absolutely couldn't, because it would instantly fall through the Earth, through the planet's core, and out the other side. It would feel infinitely heavy, not really heavy or extremely heavy, literally infinitely heavy in any meaningful human sense, because its gravity would be overwhelming. And that's just the babies of the black hole family. The theoretical minimum mass primordial black holes would be even smaller, potentially approaching the Planck length, which is the smallest possible unit of distance that has any meaning in physics. We're talking about scales where quantum mechanics and gravity start fighting each other, where our understanding of reality itself starts to fray at the edges. What strikes me most about primordial black holes isn't just their extreme properties. It's the fact that they represent a direct link to the universe's origin. If they exist, they're time capsules from the moment of creation, unchanged and unaging, carrying information about conditions that existed when the cosmos was less than a second old. Every other object we observe has changed over time. Stars burn through their fuel and evolve. Galaxies merge and transform. Planets cool and shift. But a primordial black hole, it would be essentially identical now to how it was 13.8 billion years ago. The transition to certainty. So we've explored these theoretical ancient entities, these possible dark matter candidates, these mountain mass objects compressed into spaces smaller than atoms. But now it's time to shift gears, because while primordial black holes are fascinating, they're still hypothetical. We haven't detected one with absolute certainty. The evidence is suggestive, but not definitive. But don't worry, the universe has plenty of black holes we know for sure exist. These are the stellar black holes, formed not in the Big Bang's first microsecond, but in the deaths of massive stars. These are the black holes we've detected through their gravitational effects, the ones we've watched devour their companion stars, the ones that occasionally collide and send ripples through space-time itself. And here's what's amazing. Even though these stellar black holes formed from regular cosmic processes, even though they started as normal stars burning in normal galaxies, they're no less extreme than their theoretical primordial cousins. In fact, some of them are so violent, so actively destructive, that they make primordial black holes seem downright peaceful by comparison. Picture a black hole that's currently in the process of eating a star 70 times more massive than our Sun. Every day, huge chunks of that doomed star get ripped away by tidal forces and spiral into the black hole's maw. The friction as this stolen matter accelerates toward the event horizon heats it to millions of degrees, making it shine brighter than 500,000 suns. And this isn't theoretical. This is actually happening right now while you're reading this, in a galaxy called Messier 33. That's where we're headed next. To the black holes we can see destroying stars in real time. To the cosmic monsters born from supernova explosions. Two objects so dense that a teaspoon of their material would outweigh Mount Everest. These are the stellar black holes, and they're about to show us that reality can be just as extreme as any theory. What kind of cosmic violence does it take to create a black hole from a dying star? How do these objects grow from stellar remnants into galaxy-tinged giants? And what happens when two black holes collide at nearly the speed of light? The answers are coming up, and trust me, they're even more incredible than you might imagine. Part 2. Stellar black holes, the violent birth of cosmic monsters. We've explored the theoretical realm of primordial black holes, those ancient entities potentially hiding in the universe's shadows. But now we're stepping into territory where theory meets brutal, observable reality. Stellar black holes aren't hypothetical. They're not mathematical curiosities. They're the confirmed remnants of stellar death, and they're absolutely everywhere in our galaxy. Here's the fundamental challenge the universe faces. How do you compress matter so intensely that it collapses into itself and becomes a black hole? In today's universe, you can't just squeeze something really hard and hope it turns into a black hole. You need truly catastrophic conditions. We're talking about events so violent that they rank among the most powerful phenomena in the entire cosmos. Only two scenarios in the modern universe can generate the necessary conditions. Either the core of a supermassive star collapses during a supernova explosion, or two neutron stars collide and merge. Let's paint a picture of what actually happens during a supernova. Imagine a star that's been burning for millions of years, fusing hydrogen into helium, helium into carbon, carbon into heavier elements, working its way up the periodic table. For its entire life, the star has maintained a delicate balance. The outward pressure from nuclear fusion pushes against the inward pull of gravity. It's a cosmic tug-of-war that can last for eons. But eventually, inevitably, the star runs out of fuel. When that happens, the balance shatters instantly. There's no more outward pressure to counteract gravity. The star's core, containing more mass than our entire sun compressed into a sphere the size of a city, collapses in less than a second. The outer layers come crashing down, then rebound off the incompressibly dense core and explode outward at roughly 10% the speed of light. The explosion releases more energy in a few seconds than our sun will produce in its entire 10 billion year lifetime. And what's left behind? A black hole, a wound in space-time itself. Size comparisons that break your brain. To understand stellar black holes, we need a unit of measurement. Let's use our sun, which weighs about 2,000 trillion kilograms. That's A2 followed by 30 zeros. Already we're dealing with numbers that make your head spin. But this is just our baseline, our unit of comparison. Because the smallest known black hole masses about 2.7 times what our sun weighs. Now, you'd think something with nearly 3 times the sun's mass would be enormous, right? The sun itself is about 1.4 million kilometers across. You could fit over 100 Earths side by side along its diameter. So surely a black hole with almost 3 solar masses would be even bigger. Not even close. This black hole measures only 16 kilometers in diameter. That's about the distance you could comfortably walk in a few hours. It's roughly the size of Paris. Imagine the entire mass of almost 3 suns. All that matter, all that crushing weight, compressed into a sphere you could drive across in about 10 minutes on a highway. That's the density we're dealing with here. That's the reality of black holes. And here's what really messes with your mind. This isn't even particularly impressive by black hole standards. The black hole companion to a red giant star called V723 is only 17.2 kilometers wide, tiny, minuscule by cosmic standards. Meanwhile, the star it's orbiting is 24 times larger than our sun, with a diameter of about 30 million kilometers. That's a star so big you could fit almost 200 suns inside it. But guess what? This 17-kilometer black hole is bullying that giant star like it's nothing. The black hole's gravity is so intense that it's literally throwing this massive star around like a toy. The star, despite being millions of times larger in physical size, is completely at the mercy of this tiny point of crushed matter. If you could somehow watch this system from a distance, you'd see a colossal ball of burning gas being whipped around by something so small you could barely even represent it in the same image. It's David and Goliath, except David is actually the overwhelmingly more powerful entity, the star eaters among us. Let's talk about M33X7, because this black hole deserves special attention. Right now, as we speak, it's in the middle of eating a star. Not metaphorically, literally devouring it, bite by bite, day by day. The victim is a blue giant star with a mass of about 70 suns. Under normal circumstances, this star would live a relatively peaceful life for a few million years before eventually exploding as a supernova. But it's not going to get that chance, because its companion is a black hole with 15.6 times the Sun's mass, measuring just 92 kilometers across, about the size of Corsica. This island-sized monster is slowly but inevitably consuming its stellar companion. Here's how it works. The black hole's gravity creates tidal forces so powerful that they literally rip material away from the star's surface. Think of how the moon creates tides on Earth by pulling more strongly on the side of our planet facing it. Now amplify that effect by billions of times. Huge streams of gas get pulled away from the star and begin spiraling toward the black hole. As this stolen matter circles closer and closer to the event horizon, friction between different layers of the swirling gas heats everything up. We're not talking about fire here. We're talking about temperatures reaching millions of degrees, so hot that the gas emits X-rays. The entire accretion disk around the black hole shines with incredible intensity. How intense? 500,000 times brighter than our sun. Let that sink in. A black hole that's only 92 kilometers wide is generating more light than 500,000 suns. Not because the black hole itself produces light, nothing escapes from inside the event horizon, but because the process of matter falling into it releases so much energy that it outshines entire regions of the galaxy. It's one of the most efficient energy conversion processes in the entire universe. Matter falling into a black hole converts about 10% of its mass directly into energy. For comparison, nuclear fusion, the process that powers stars, only converts about 0.7% of mass to energy. The growth mechanism, eating and merging. So we've established that stellar black holes can form from dying stars, and they can grow by consuming their companion stars. But there's a problem with this growth strategy. It's slow, painfully slow on cosmic timescales. Even a black hole actively eating a massive star might only gain a few solar masses over millions of years. That's because stars are actually mostly empty space. They're huge, but most of their volume is just hot gas spread out over enormous distances. If black holes only grew by eating stars one at a time, they'd never reach the truly colossal sizes we observe in the universe. The universe simply isn't old enough. Even if a stellar black hole started consuming stars non-stop from the moment it formed, it couldn't grow to millions or billions of solar masses in just 13.8 billion years. So how do black holes get really big? They merge with each other, and when two black holes collide, the results are nothing short of spectacular. We only recently developed the technology to detect these mergers. Gravitational wave observatories like LIGO and Virgo can pick up the ripples in space-time that occur when massive objects accelerate violently, and in the past decade, these instruments have revolutionized our understanding of black holes. We're discovering mergers happening all the time, all across the universe. Here's one that really captures the imagination. Two massive black holes in a galaxy 17 billion light-years away. These weren't small, stellar black holes. These were beasts, each with dozens of solar masses. They'd been orbiting each other for who knows how long, gradually spiraling closer and closer as they radiated gravitational waves. Then, finally, they collided. The merger happened in a fraction of a second. These two objects, each with such powerful gravity that nothing could escape them, slammed together at a significant fraction of the speed of light. The collision was so violent, so energetic, that it released more energy in gravitational waves than all the stars in the Milky Way produce as light in over 4,000 years. Wrap your head around that. More energy in a fraction of a second than 100 billion stars produce in 4 millennia. And what emerged from this cosmic train wreck? A new black hole with 142 solar masses and a diameter roughly equal to Germany. One instant of incredible violence, and suddenly the universe has a black hole that would have taken millions of years to form through star consumption alone. The mysterious gap nobody expected. But here's where things get really weird. As we've surveyed the black hole population in our galaxy and beyond, we've noticed something strange. There are lots of stellar black holes with masses up to about 150 suns. We find them all over the place. But then, suddenly, nothing. A complete gap. No black holes with 200 solar masses. No black holes with 500 solar masses. No black holes with 1,000 solar masses. The next black holes we find jump straight to millions of solar masses. It's like finding a bunch of houses, then some mansions, and then suddenly skyscrapers, with absolutely nothing in between. No medium-sized buildings, just a huge empty gap in the size distribution. This is really puzzling because our understanding of how black holes grow suggests they should exist at all sizes. If they grow by eating stars and merging with each other, why don't we see any black holes in this middle range? What's stopping them from existing? Or are they out there, just really hard to detect for some reason we haven't figured out yet? Think about the implications here. We're missing an entire class of objects. It's as if someone went through the universe and removed all the black holes between 150 and 1 million solar masses. But who, what, why? Nature doesn't usually leave such obvious gaps in its creations. When we see a missing link in any chain, it usually means we're fundamentally misunderstanding something about the process. Some scientists think the gap might be real, caused by the way massive stars collapse. There might be an upper limit to how big a stellar black hole can get from a single star's death. Beyond a certain mass, maybe stars explode completely instead of leaving behind a black hole. But that doesn't explain why mergers haven't filled in the gap. 275 solar mass black holes merging should create a 150 solar mass black hole right in the middle of the gap. Yet we don't see them. Other researchers suggest the gap might be an observational illusion. Maybe these intermediate mass black holes do exist, but they're lurking in places where we can't easily detect them. Perhaps they're floating freely through intergalactic space, not actively feeding on anything, completely invisible to our instruments. That's entirely possible. After all, we can only detect black holes when they're doing something noticeable, like eating a star or merging with another black hole. The need for supermassive seeds. Here's the real problem. When we look at the centers of distant galaxies whose light has taken billions of years to reach us, we see supermassive black holes already fully formed. We're talking about black holes with millions or even billions of solar masses, existing when the universe was less than 1 billion years old. And that shouldn't be possible. Do the math. If a stellar black hole starts with 10 solar masses and grows by eating stars, how long would it take to reach 1 million solar masses, even under ideal conditions? With a constant supply of stars to consume and assuming the black hole can eat as fast as physically possible without the radiation pressure blowing away incoming matter, it would take hundreds of millions of years at minimum. More realistically, it would take billions of years. But these ancient supermassive black holes don't have billions of years. The universe itself was barely a billion years old when they formed. It's like finding a full-grown oak tree in a garden that was planted last week. The timeline doesn't add up. Something is seriously wrong with our understanding of how supermassive black holes formed. This is where the stellar black holes we've been discussing stop being just interesting objects in their own right and start being pieces of a much larger puzzle. If supermassive black holes can't form from stellar black holes eating stars, then maybe they formed from something else entirely. Maybe there was a special process in the early universe that could create much larger seed black holes, massive enough to grow into supermassive black holes in the available time. We need something that can give black holes a head start. We need black holes that don't start at 10 or 20 solar masses, but at thousands or tens of thousands of solar masses. We need a cosmic shortcut. And that's where things get really interesting, because some scientists think they might have figured out what that shortcut was. Quasi-stars, the bridge to something bigger. Before we dive into the truly colossal black holes at the centers of galaxies, take a moment to appreciate where we are in this journey. We started with primordial black holes, theoretical objects from the universe's first, second. Then we moved to stellar black holes, confirmed objects formed from dying stars, ranging from 16 kilometers to hundreds of kilometers across. We've seen them eating stars, merging with each other, and releasing more energy in seconds than our sun produces in millennia. But we've also hit a wall. Stellar black holes, no matter how we slice it, can't explain the existence of supermassive black holes. The numbers simply don't work. Which means we're missing something fundamental about how black holes grow. We're missing a crucial chapter in the story of how the universe's smallest dense objects become its largest single structures. And here's what makes this so exciting. We're living at the exact moment in history when we might actually solve this mystery. New telescopes are coming online that can peer deeper into the universe's past than ever before. Gravitational wave detectors are getting more sensitive every year. Computer simulations are becoming sophisticated, enough to model the formation of the first stars and galaxies in exquisite detail. We're on the verge of understanding how stellar black holes bridge the gap to supermassive ones. We're about to uncover the secrets of the universe's most extreme growth process. And the answer might involve stars so massive, so unlike anything we see today, that they barely seem possible. Stars that could have black holes at their cores, while still shining like normal stars. Stars that could have been the seeds for the universe's greatest monsters. What were these quasi-stars? How big could they grow? And how did they create the supermassive black holes we see dominating galactic centers? The answers are coming next. And they're going to challenge everything you thought you knew about how stars and black holes work. Part 3. Quasi-stars and supermassive black hole seeds. When stars become black hole factories. We've hit a cosmic mystery that demands an extraordinary solution. The universe is filled with supermassive black holes containing millions or billions of times our sun's mass. Yet the universe is only 13.8 billion years old. Stellar black holes, no matter how efficiently they eat or merge, simply can't grow fast enough to explain these giants. We need something radically different. We need a mechanism that can jumpstart black hole growth in the early universe. We need quasi-stars. But before we dive into what quasi-stars are, let's really understand the scale problem we're trying to solve. When we observe distant galaxies, we're looking back in time because light takes time to travel. A galaxy 10 billion light-years away shows us what it looked like 10 billion years ago. And when we look at these ancient galaxies, galaxies that formed when the universe was less than 1 billion years old. We find supermassive black holes already sitting at their centers with millions of solar masses. This is absurd. It's like planting a seed yesterday and finding a giant redwood tree today. The growth rate required is almost physically impossible. Even if a stellar black hole ate continuously at the maximum possible rate, converting every scrap of matter it encountered into additional mass, it would still fall short. The universe simply hasn't existed long enough for this kind of growth starting from stellar black holes. So scientists started asking uncomfortable questions. What if stellar black holes weren't the beginning? What if there was something earlier, something bigger, something that could give black holes a massive head start? What if the early universe could produce black holes that started with thousands of solar masses instead of tens? Enter the quasi-star hypothesis. And trust me, these things are absolutely bonkers. Stars that shouldn't exist, but might have anyway. To understand quasi-stars, we need to travel back to the early universe, maybe 100 million years after the Big Bang. The universe looked very different then. There were no planets, no complex molecules, no heavy elements beyond a little bit of lithium. The universe was filled almost entirely with hydrogen and helium, the two simplest elements, floating in vast clouds throughout space. But here's the key difference from today, that hydrogen and helium was incredibly dense compared to what we see in modern space. The universe was smaller, more compressed, and matter was packed together much more tightly. This created conditions that simply don't exist anymore. In today's universe, when gas clouds collapse to form stars, they fragment into many smaller pieces. You don't get single, giant stars. You get clusters of smaller stars. But in the early universe, the physics was different. Those dense hydrogen clouds could collapse into single massive objects without fragmenting. They could form stars with masses thousands of times greater than our Sun. These would be the quasi-stars, and they'd make even the most massive stars we see today look like tiny candles. Let's get a sense of scale here. The biggest stars in the modern universe, stars like UY Scuti or Stephenson 218, are absolute monsters. Our Sun is literally like a grain of sand compared to them. If you replaced our Sun with one of these giants, its surface would extend past the orbit of Jupiter. That's how big modern supergiant stars can get. Now imagine something that makes those giants look small. Quasi-stars could have been 10,000 times the mass of our Sun or more. Their cores alone would contain more mass than the largest complete stars we see today. These wouldn't just be big stars. They'd be fundamentally different objects, operating under rules that modern stars can't access. The deadly balance inside a quasi-star. Here's where quasi-stars get really weird. Normally, when you pack that much mass together, it should immediately collapse into a black hole. The gravity would be so intense that nothing could stop the collapse. Modern stars can resist this because nuclear fusion in their cores creates outward pressure that balances gravity, but there's a limit. Once a star gets too massive, even fusion pressure can't hold it up anymore. So how could a quasi-star exist without immediately collapsing? The answer is both elegant and terrifying. It has a black hole at its core already. But it doesn't collapse completely because the black hole actually stabilizes the star through a bizarre process. Picture this. You've got thousands of solar masses of hydrogen and helium trying to collapse. The very center gives in to gravity and forms a black hole. Maybe it starts at just 10 or 20 solar masses. But now, something interesting happens. Material from the star falls toward the black hole, accelerating to enormous speeds. The friction and compression heat this in falling matter to millions of degrees. This creates intense radiation that pushes outward, not just from the black hole itself, but from the incredibly hot material spiraling into it. This outward radiation pressure counteracts gravity, at least partially. It creates a deadly equilibrium. Gravity pulls the star inward, feeding the black hole. The black hole grows and produces more intense radiation. That radiation holds up the outer layers of the star, preventing complete collapse. The star keeps feeding the black hole, and the black hole keeps holding up the star. It's a cosmic feedback loop that could last for millions of years. Think about how bizarre this is. The black hole isn't destroying the star. It's keeping it alive. Without the black hole at its core, the quasi-star would collapse completely. But with the black hole there, feeding and growing, the star maintains a stable structure. It's like a balloon where the air inside is a black hole. The balloon stays inflated not in spite of the black hole, but because of it. Growing giants in the cosmic dawn. Now let's talk about growth rates, because this is where quasi-stars solve our supermassive black hole problem. A normal stellar black hole eating a star might gain a few solar masses over millions of years. It's slow, steady, and completely inadequate for explaining early supermassive black holes. But a black hole inside a quasi-star? That's a completely different story. The black hole sits at the center of thousands of solar masses of fuel. It's literally embedded in a buffet that surrounds it completely. There's no hunting for food. There's no waiting for a companion star to wander close enough. The black hole is constantly fed by the immense pressure of the star's outer layers pushing inward. Material streams toward the event horizon in a never-ending flow. Under these conditions, a black hole could grow at rates that seem impossible by modern standards. Instead of gaining a few solar masses per million years, it could gain hundreds or thousands. Instead of taking billions of years to reach a million solar masses, it might only take a few million years. That's fast enough to explain how we get supermassive black holes in the early universe. Let's do some rough math here. Start with a 20 solar mass black hole inside a quasi-star with 10,000 solar masses. If the black hole can consume just 1% of the star's mass over a million years, that's 100 solar masses of growth. Keep that rate going for 10 million years, and you've got 1,000 solar mass black hole. Let it feed for 50 million years, and you could hit 5,000 solar masses or more. And here's the beautiful part. The quasi-star doesn't need to last forever. Once the black hole consumes enough of the star's mass, the balance tips. The radiation pressure can no longer hold up the outer layers. The remaining material collapses onto the black hole in a final feeding frenzy. What you're left with is a black hole with thousands of solar masses, far larger than any stellar black hole could reach through normal processes. These massive seed black holes would be perfect candidates for growing into the supermassive black holes we see today. They'd have the head start needed to reach millions or billions of solar masses within the universe's lifetime. Problem solved, mystery explained. Or is it? The evidence problem and alternative theories. Here's the uncomfortable truth. We don't actually know if quasi-stars existed. We've never observed one. We can't observe one because, even if they formed in the early universe, they'd be long gone by now. They would have consumed themselves and left behind only their black hole cores billions of years ago. So we're proposing the existence of objects we can never directly detect to explain a problem we definitely have. This bothers some scientists. It feels a bit too convenient, too much like making up an invisible solution to a visible problem. And they're right to be skeptical. Science demands evidence. not just clever theories. So what evidence do we have for quasi-stars? Honestly, not much direct evidence. But we have plenty of indirect reasoning. We know the early universe was denser. We know it could form more massive objects than today's universe can. We know that mathematical models of quasi-stars work. They're physically plausible, even if we can't prove they existed. And most importantly, we know we need some mechanism to explain fast black hole growth in the early universe. Quasi-stars fit the bill perfectly. But maybe there are other explanations. Some scientists think supermassive black holes could have formed directly from collapsing gas clouds without ever being stars at all. These would be direct collapse black holes, forming with thousands or even millions of solar masses in one catastrophic event. No quasi-star phase needed. Just a massive cloud of gas that skips the star stage entirely and goes straight to black hole. Others propose that the first generation of stars might have been even more massive than quasi-stars, but short-lived. These population 3 stars, made of pure hydrogen and helium with no heavier elements, might have reached masses of hundreds of thousands of suns before exploding and leaving behind massive black hole remnants. We've never seen a population 3 star either, but we know they must have existed because something had to create the first heavy elements. Here's what fascinates me about this debate. We're arguing about objects so massive and so ancient that they make stellar black holes look commonplace. We're trying to understand processes that happened when the universe was barely 1% of its current age. And we're doing this not with direct observations, but with computer simulations, mathematical models, and theoretical physics. It's some of the most challenging science humanity has ever attempted. The first seeds of today's giants. Whether quasi-stars existed or some other mechanism created massive seed black holes. One thing is clear. The early universe found a way to jumpstart black hole growth. Those seeds, however they formed, became the foundation for the supermassive black holes dominating galaxies today. And that brings us to an interesting question about cosmic evolution. Think about the sequence of events. First, somehow, the universe creates black holes with thousands of solar masses. These seeds settle into the centers of forming galaxies. As galaxies grow and merge, the black holes at their centers also merge, combining their masses. Meanwhile, gas flows toward the galactic center, feeding the black holes, making them even larger. Over billions of years, through countless mergers and feeding events, these seed black holes grow into the supermassive monsters we observe today. It's a compelling narrative. From quasi-stars to supermassive black holes in a few billion years. From thousands of solar masses to billions of solar masses, through a combination of merging and feeding. The timeline works. The physics makes sense. We can trace a plausible path from the early universe to today. But here's where it gets really mind-bending. This process might still be happening. Some galaxies might still contain intermediate mass black holes. The modern descendants of quasi-star seeds that haven't fully grown yet. These would be the black holes in the mysterious gap we discussed earlier, the ones between 150 and 1 million solar masses. Maybe they're not missing. Maybe they're just rare, lurking in small galaxies or dwarf galaxies that haven't merged with larger structures yet. If we could find these intermediate mass black holes, it would provide crucial evidence for the quasi-star theory. It would show us black holes caught in the act of growing from seeds to supermassive giants. But they're incredibly hard to detect because they're not massive enough to dominate large galaxies, yet too massive to form from individual stars. They occupy an awkward middle ground that makes them almost invisible to our current instruments. The scale of impossibility made possible. Let's step back and really absorb what we're discussing here. We're talking about stars that contained black holes at their cores while still functioning as stars. Stars where the central engine isn't nuclear fusion but gravitational collapse. Stars that fed their own destroyers for millions of years before finally succumbing. These concepts challenge our basic understanding of what a star even is. A normal star is a nuclear fusion reactor held together by gravity. It produces energy by combining light elements into heavier ones. The fusion happens at the core, and the energy gradually diffuses outward until it reaches the surface and radiates into space. Simple, elegant, well understood. A quasi-star would be something else entirely. Its energy wouldn't come primarily from fusion, though fusion might still happen in the outer layers. Instead, the primary energy source would be gravitational potential energy released as matter falls into the central black hole. This is actually a more efficient process than fusion, converting a higher percentage of mass into energy. But it requires a black hole, and black holes don't naturally exist inside stars in the modern universe. Can you imagine if we could somehow observe a quasi-star in action? Watching it from a safe distance, you'd see what looks like an incredibly bright star, possibly the brightest object in its entire region of space. But unlike a normal star, which shines steadily for millions or billions of years, a quasi-star would be dynamic, changing, evolving rapidly. Material would flow into the center at variable rates. The black hole would grow, altering the balance of forces. The star might flicker or pulse as the feedback mechanisms adjusted. And if you could somehow see inside it, past the blinding outer layers, you'd witnessed something never seen in nature today. A black hole surrounded by a dense envelope of hot gas, the two locked in a deadly embrace, neither able to exist without the other. The black hole needs the star's mass to grow. The star needs the black hole's radiation to stay inflated. Remove either component, and the whole system collapses, bridging past and present. The quasi-star hypothesis does more than just explain how supermassive black holes formed quickly. It connects to very different eras of cosmic history. The early universe, dominated by hydrogen and helium, where the first structures were forming and the rules were different from today, and the modern universe, filled with galaxies containing supermassive black holes at their centers, where heavy elements exist and stars form according to familiar processes. Quasi-stars would be the bridge between these eras. They'd represent the transition from a universe of simple gases to a universe of complex structures. The black holes they created would become the organizational centers of galaxies, even though they only contain a tiny fraction of a galaxy's total mass. Every supermassive black hole in every galaxy might trace its lineage back to a quasi-star or similar object in the early universe. And here's something to consider. If quasi-stars could form in the early universe, could they form again under the right conditions? Probably not in any galaxy we can observe, because the conditions are too different now. But perhaps in some extreme environment we haven't thought of. Some cosmic scenario we haven't yet imagined. The physics of quasi-stars could emerge again. The universe is vast and old. It's had a lot of time to try out different combinations of matter and energy. What we do know is that the early universe was wild, experimental, testing possibilities that don't exist anymore. Quasi-stars might be just one of many exotic objects that formed in those first 100 million years. There could be other strange entities we haven't even theorized yet. Other solutions to other problems, other bridges between stellar phenomena and supermassive structures. The road to supermassive dominance. We've journeyed from stellar black holes through the theoretical landscape of quasi-stars. We've explored how the early universe might have created the seeds needed for rapid black hole growth. Now we're ready to see the results of billions of years of evolution. We're ready to examine the supermassive black holes themselves. The kings of the cosmic hierarchy, the largest single objects in existence. These giants sit at the centers of galaxies containing millions or billions of solar masses, dominating their surroundings with gravity so intense it shapes the very structure of galaxies. They're fed by streams of gas flowing inward from the galaxy. They occasionally devour entire stars that wander too close, and when two galaxies merge, their central black holes eventually merge too, creating even more massive monsters. But here's what makes them fascinating beyond just their size. Supermassive black holes aren't passive objects. They interact with their galaxies in complex ways. They regulate star formation by heating gas and blowing it away. They create jets of matter traveling at nearly light speed. They generate enough energy to outshine all the stars in their galaxy combined. They're not just sitting there growing. They're actively shaping cosmic evolution. The quasi-stars we discussed, if they existed, would have been the ancestors of these giants. The seed black holes they created would have spent billions of years growing, merging, feeding, until they reached their current gargantuan sizes. And the process isn't over. Supermassive black holes are still growing today, still merging when galaxies collide, still feeding on gas and stars that stray too close. What do these supermassive black holes actually look like? How big can they grow? And what happens when they actively feed, creating some of the brightest objects in the entire universe? The answers are coming in the next section, and they're going to show you that even after everything we've discussed, we've only scratched the surface of how extreme black holes can actually get. Part 4. Supermassive black holes, the kings of the universe have arrived. We've climbed the ladder of cosmic extremes, from primordial specks to stellar remnants to theoretical giants called quasi-stars. Now we're reaching the pinnacle. We're entering the realm of supermassive black holes, the undisputed monarchs of the universe. These are objects so massive, so incredibly enormous, that they make everything we've discussed so far look almost quaint by comparison. And the wild part, they're everywhere. Almost every large galaxy in the universe has one sitting right at its center. Let's start close to home, right at the heart of our Milky Way galaxy. About 26,000 light-years from Earth, there's a supermassive black hole called Sagittarius A star. For decades, we couldn't see it directly, but we could watch stars orbiting something invisible. Something with such powerful gravity that it whipped those stars around at thousands of kilometers per second. Stars with masses comparable to our Sun, racing through their orbits in just years, instead of the millions of years you'd expect. By carefully tracking these stellar orbits over decades, astronomers calculated exactly how massive the invisible object must be. The answer: about 4 million times the mass of our Sun. 4 million suns worth of matter, all compressed into a region of space with a radius just 17 times larger than our Sun. That's smaller than most giant stars, yet millions of times more massive. The density is incomprehensible. But here's what's really interesting about Sagittarius A star. It's surprisingly calm. It's not actively devouring huge amounts of matter. It's not blasting out jets of radiation. It's just sitting there, quietly dominating the galactic center through pure gravitational presence. Most of the time, it's actually pretty dim by supermassive black hole standards. It occasionally flares up when something wanders too close and gets shredded. But overall, it's what we'd call a quiescent black hole, sleeping but not dead. And that raises a fascinating question. If our galaxy's supermassive black hole is this calm, what about the ones that aren't? The misconception about galactic anchors. Before we dive into the violent supermassive black holes, we need to clear up a huge misconception that almost everyone has about these objects. When people hear that there's a supermassive black hole at the center of every galaxy, they naturally assume it's like the sun in our solar system. They picture the black hole as a massive anchor holding everything together, with all the stars gravitationally bound to it, orbiting around it like planets around the sun. That mental model is completely wrong, and understanding why it's wrong tells us something profound about how galaxies actually work. Here's the key fact. Our sun contains 99.86% of all the mass in the solar system. The planets, asteroids, comets, and everything else combined make up just a tiny fraction. That's why the sun dominates. That's why everything orbits it. Its mass is so overwhelming that it defines the entire system's structure. But supermassive black holes, they typically contain only 0.001% of their galaxy's total mass. Think about that. Sagittarius A star has 4 million solar masses. The entire Milky Way contains about 200 billion stars, plus vast amounts of gas, dust, and dark matter. The black hole is massive by any normal standard, but compared to the galaxy as a whole, it's almost nothing. It's like a grain of sand on a beach, thinking it controls the entire coastline. So, if the supermassive black hole doesn't hold the galaxy together, what does? The answer is dark matter. Galaxies are embedded in enormous halos of dark matter that extend far beyond the visible stars. It's this dark matter, with its gravitational influence, that keeps galaxies from flying apart. The stars aren't orbiting the black hole. They're orbiting the combined gravitational center of the entire galaxy, which is dominated by dark matter, not by the central black hole. This doesn't mean supermassive black holes are unimportant. Far from it. Even though they're a tiny fraction of the galaxy's mass, they have a disproportionate influence on their surroundings. They regulate star formation. They heat gas in the galactic center. When they're actively feeding, they can affect the entire galaxy's evolution. But they're not gravitational anchors. They're more like cosmic thermostats, controlling the temperature and energy flow of the galactic center. When feeding giants create hell, not all supermassive black holes are as polite as Sagittarius A star. Some are actively feeding on massive amounts of material, and when that happens, they become some of the most violent objects in the universe. Let me introduce you to the supermassive black hole at the center of a galaxy called BL Lacertae. This monster is currently gorging itself on clouds of gas and dust in its galaxy. Material spirals inward, forming an accretion disk that glows with incredible intensity. The friction and compression in this disk heat the infalling matter to millions of degrees. But that's just the beginning. The black hole's intense magnetic fields channel some of this material into narrow jets that shoot outward from the poles at 98% the speed of light. These aren't gentle streams. These are cosmic flamethrowers, beams of plasma carrying more energy than you can imagine. If Earth somehow found itself orbiting this black hole instead of our sun, the sky would be dominated by a disk 115 times larger than the sun appears to us, and we wouldn't last long enough to appreciate the view. The radiation from the accretion disk would incinerate our planet in seconds. The surface of Earth would literally boil away into space. This is what an actively feeding supermassive black hole looks like. This is nature at its most extreme. And BL Lacertae isn't even particularly large by supermassive black hole standards. It's just hungry. It's taking full advantage of the available matter in its vicinity, converting that matter into energy with brutal efficiency. Now let's talk about Cygnus A, because this is where supermassive black holes start to become truly incomprehensible in scale. The black hole at the center of Cygnus A contains 2.5 billion solar masses. Not million, billion. That's 2,500 million times the mass of our Sun, and its event horizon, the point of no return, stretches 14.7 billion kilometers across. To put that in perspective, if you replaced our Sun with the Cygnus, a black hole, it would swallow Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, and reach halfway to Uranus. It would consume everything out to about halfway through our solar system. The Earth wouldn't just be inside the event horizon. We'd be nowhere near the edge. We'd be deep inside, already falling toward the singularity, with no possibility of escape or rescue. The radio lobe phenomenon that defies belief. But the Cygnus, a black hole's size, isn't even its most impressive feature. What really blows my mind is what it's doing to its surroundings. This black hole is consuming so much matter that it's created a magnetic funnel effect in its accretion disk. The disk doesn't just glow. It channels material into jets, similar to Biel Lacerté, but on a much larger scale. These jets shoot out from the black hole's poles and plow into the intergalactic medium, the thin gas between galaxies. When these jets hit the surrounding gas, they don't just push it aside, they inflate enormous bubbles called radio lobes. And when I say enormous, I mean they tower over the entire galaxy. These lobes extend 500,000 light-years from end to end. That's the width of 2.5 Milky Way galaxies placed side by side. Let that sink in. The black hole itself is 15 billion kilometers across. But the structures it's creating span 500,000 light-years. That's a ratio of scale that's hard even to comprehend. It's like a basketball creating ripples that extend across an entire continent. The black hole is using its gravitational and magnetic power to reshape space on scales that dwarf entire galaxies. And here's the really fascinating part. We can see these radio lobes. They emit radio waves that our telescopes can detect. They're some of the largest structures associated with individual objects that we know of in the universe. They're proof that supermassive black holes, despite containing only a tiny fraction of their galaxy's mass, can influence their environment on truly cosmic scales. This is what I mean when I say supermassive black holes punch above their weight class. Yes, they're only 0.001% of the galaxy's mass, but that 0.001% is concentrated in such a small volume and organized in such a powerful way that it can dominate the energy budget of the entire galactic center. It's not about total mass. It's about density, organization, and the incredible efficiency of gravitational energy conversion. The first photograph of darkness itself. In 2019, humanity achieved something remarkable. For the first time in history, we took a photograph of a black hole, not an artist's impression, not a simulation, an actual image of a black hole's shadow. And the black hole we photographed sits in the galaxy Messier 87, about 55 million light-years from Earth. The Messier 87 black hole contains 6.5 billion solar masses. It's heavier than Cygnus A, and its shadow covers our entire solar system. If you could somehow position this black hole where our Sun is, its event horizon would extend past Neptune's orbit. Every planet, every dwarf planet, every comet in our solar system would be inside the point of no return. But what we actually photographed wasn't the black hole itself. You can't photograph a black hole directly because no light escapes from inside the event horizon. What we captured was the shadow of the black hole silhouetted against the glowing accretion disk behind it. The disk emits radio waves as matter spirals inward at nearly light speed. The black hole blocks some of those radio waves, creating a dark circular region in the image. That photograph represents an incredible technical achievement. We essentially created a telescope the size of Earth by linking radio observatories around the globe. This network, called the Event Horizon Telescope, collected data for days, synchronized to billionths of a second. Then teams of scientists spent years processing that data, checking their work, making sure they hadn't made any errors. The result was an image showing a dark circle surrounded by a glowing asymmetric ring. Why asymmetric? Because the accretion disk is rotating at relativistic speeds. The side rotating toward us appears brighter due to relativistic beaming, where matter moving toward you at nearly light speed appears brighter than matter moving away. It's a direct visual confirmation of Einstein's predictions about how matter behaves near massive objects, its theory transformed into observable reality. The difference between calm and chaos. Looking at supermassive black holes, you start to notice something interesting. They come in two basic varieties: the quiet ones, like Sagittarius A star, and the violently active ones, like BL Lacertae and Cygnus A. What makes the difference? Why are some supermassive black holes peaceful, while others are cosmic catastrophes? The answer is surprisingly simple. Food, or more precisely, the availability of matter to consume. Sagittarius A star is calm because there's not much gas flowing into the galactic center right now. The Milky Way's central regions are relatively empty. Stars pass near the black hole, but stars are small targets and mostly empty space. The black hole can't just reach out and grab them. It has to wait for something to wander close enough to be captured by its gravity. But galaxies like BL Lacertae and Cygnus A have lots of gas in their central regions. Maybe they recently merged with other galaxies, dumping fresh gas into the center. Maybe they have active star formation regions feeding material inward. Whatever the reason, their supermassive black holes have access to abundant fuel, and when a supermassive black hole has fuel, it doesn't hold back. It feeds voraciously, creating accretion disks, jets, and radio lobes. This tells us something important about galactic evolution. Supermassive black holes alternate between active and quiet phases throughout their lives. Billions of years ago, our Milky Way's black hole was probably much more active. It probably had a bright accretion disk and jets. But over time, it consumed the available gas, and now it's in a quiet phase. Billions of years in the future, if the Milky Way merges with Andromeda as predicted, Sagittarius A star might become active again, fed by gas stirred up during the merger. Black holes don't change their fundamental nature. They're always black holes, always dominated by gravity, always trapping light beyond the event horizon. But their appearance changes dramatically based on how much they're eating. A feeding supermassive black hole can outshine all the stars in its galaxy. A starved one is nearly invisible. Same object, radically different, observable properties. The question of influence and control. Here's something that keeps astronomers up at night. How exactly do supermassive black holes regulate star formation in their galaxies? We know they do it. The evidence is clear. Galaxies with very massive central black holes tend to have less active star formation. The black hole somehow suppresses the formation of new stars throughout the galaxy, but the mechanism is still debated. The leading theory involves something called AGN feedback. where AGN stands for active galactic nucleus. When a supermassive black hole actively feeds, it doesn't just create jets. It also creates powerful winds that blow outward from the accretion disk. These winds can be strong enough to push gas out of the galaxy entirely, or at least heat it to temperatures where it can't collapse to form stars. No gas, no star formation. Problem solved? But here's the weird part. The black hole is only 0.001% of the galaxy's mass. How does something that small regulate processes throughout a structure 100,000 light-years across? It's like a tiny thermostat in one corner of a building somehow controlling the temperature in every room. The scale of influence seems disproportionate to the size of the object, yet the evidence says it happens. And that tells us something profound. In the universe, it's not always about raw mass. It's about concentration, organization, and energy density. A supermassive black hole might be tiny compared to its galaxy, but it's the most concentrated, most organized, most energy-dense object in that galaxy, and that gives it power far beyond what its mass alone would suggest. This is the fundamental nature of black holes. They're not just massive objects. They're singularities where the normal rules break down. They're points where infinity enters the equations. They're places where our understanding of physics reaches its limits. And yet they're real, observable, measurable. They exist in our universe, shaping galaxies, influencing cosmic evolution, growing larger with every passing moment. Beyond supermassive, a hint of what's coming. We've explored supermassive black holes from millions to billions of solar masses. We've seen them quiet and calm like Sagittarius A star. We've seen them violent and active like Cygnus A. We've even photographed one, capturing the shadow of darkness itself against a glowing background. These objects already seem impossibly large, impossibly powerful, impossibly extreme. But there's another category, a classification beyond supermassive. Black holes so large they dwarf even the giants we've been discussing. Black holes with tens of billions of solar masses. Black holes that take light a full week to cross from event horizon to singularity. Black holes that could fit 11 complete solar systems side by side inside them. These are the ultramassive black holes, and they represent the absolute peak of what nature can create. They're the largest single objects that will probably ever exist in our universe. They're so massive that even calling them supermassive seems inadequate. They demand their own category, their own terminology, their own frame of reference. And when these ultramassive black holes feed, when they actively consume matter, they create quasars. These are objects so bright they outshine 100 trillion stars. Objects visible from halfway across the observable universe. Objects that release more energy in seconds than our sun will produce in its entire 10 billion year lifetime. How did these cosmic titans form? How large is the largest one we know? And what happens when you have a black hole so massive that it has another supermassive black hole orbiting it like a planet? The final chapter of our journey awaits, and it's going to push the boundaries of what you thought was possible even further than we already have. Part 5. Ultramassive black holes and the universe's largest single bodies. When supermassive isn't enough of a description, we've reached the summit, the absolute peak of cosmic scale. We're talking about black holes so monumentally massive that even the term supermassive fails to capture their enormity. These objects have eaten so much matter, absorbed so many stars and gas clouds, merged with so many other black holes, that they've grown to tens of billions of solar masses. They deserve their own classification entirely. We call them ultramassive black holes, and they represent the largest single objects that will probably ever exist in our universe. But size isn't their only impressive feature. When ultramassive black holes actively feed, they create something called a quasar. The term comes from quasar-stellar object because astronomers initially thought they were seeing strange stars. But they're not stars. They're supermassive or ultramassive black holes surrounded by accretion disks so bright, so incredibly luminous, that they outshine entire galaxies. We're talking about brightness levels equivalent to thousands of galaxies full of stars, all emanating from a region smaller than our solar system. Think about what that means. A quasar, powered by an ultramassive black hole, can be visible from billions of light years away. We can see them across most of the observable universe. They're cosmic lighthouses, beacons shining across the void, powered not by fusion like stars, but by gravity converting matter into pure energy as it falls toward the event horizon. And that process is so efficient, so powerful, that it makes nuclear fusion look weak by comparison. The brightest quasars release more energy in 1 second than our sun produces in years. And they maintain this output for millions of years. The sheer scale of energy involved defies human comprehension. We can write the numbers down, we can do the mathematics, but truly understanding what it means for an object to shine with the brightness of 100 trillion stars, that's beyond our intuitive grasp. Our brains simply aren't wired to process scales that extreme. OJ 287, a black hole with its own black hole. Let me introduce you to one of the most mind-bending systems we've discovered. In a galaxy designated OJ 287, about 3.5 billion light-years from Earth, there's an ultramassive black hole containing 18 billion solar masses. 18 billion suns worth of matter, compressed into a singularity. Already that's almost incomprehensible. But here's where it gets really weird. This ultramassive giant has a companion. Another black hole orbits around it. And that companion isn't some tiny stellar black hole. It's a supermassive black hole in its own right, with a mass about 40 times greater than Sagittarius A star. Let that sink in. Our galaxy's central black hole, the 4 million solar mass giant that dominates the Milky Way's core, would be just a small satellite in this system. The companion black hole in OJ 287 weighs about 160 million solar masses. That's 40 times heavier than Sagittarius A star, and it's the smaller object in its system. It orbits the much larger ultramassive black hole like a planet orbits a star. This system challenges our sense of scale in fundamental ways. We're used to thinking of supermassive black holes as the ultimate objects, the top of the hierarchy, but here's a supermassive black hole relegated to secondary status, dominated by something so much larger that it's barely even in the same category. It's like finding out that Earth orbits a planet that itself orbits the Sun. Our entire frame of reference gets scrambled. The orbital dynamics of this system are fascinating. Every 12 years, the smaller black hole plunges through the accretion disk of the larger one. When that happens, the collision of matter creates a massive outburst of radiation that we can detect from billions of light years away. Astronomers have been tracking these outbursts for over a century, and they match predictions almost perfectly. It's one of the most precisely understood binary black hole systems we know of. Despite being incomprehensibly large and impossibly distant. And here's what really gets me. This entire system, both black holes together, could fit 3 complete solar systems side by side inside the larger black hole's event horizon. Not 3 planets, 3 complete solar systems, from the Sun to the Oort cloud, times 3. That's the scale of the largest black hole in this binary pair. And it's not even the largest ultramassive black hole we've found. TON 618, the King of Kings. Now we arrive at the true monster, the reigning champion of cosmic scale. A black hole so massive, so ridiculously enormous, that it makes everything else we've discussed look modest. This is TON 618, and it contains 66 billion solar masses. 66 billion. That's not a typo. That's 66,000 million times the mass of our Sun. To put this in perspective, if you could somehow count to 66 billion at one number per second, it would take you over 2,000 years. That's how many suns worth of matter this black hole contains. And all of it is compressed into a singularity, a point of infinite density surrounded by an event horizon so large it beggars belief. How large? Well, if you crossed the event horizon of TON 618, traveling at the speed of light, it would take you 1 full week to reach the singularity at the center. 1 week at light speed. Light travels about 300,000 kilometers every second. In a week, that's roughly 180 billion kilometers. The distance from the Sun to Pluto is about 6 billion kilometers. So you could fit about 30 Sun to Pluto distances inside the radius of TON 618's event horizon. Or, to put it another way, you could place 11 complete solar systems side by side, and they would all fit comfortably inside this black hole. Not squeezed together, not cramped, comfortably, with room to spare. That's the scale we're dealing with here. That's what nature can create when given enough time and enough matter. And TON 618 isn't just massive, it's actively feeding. It's a quasar, blazing with the combined light of about 100 trillion stars. We can see it from 18 billion light-years away. The light we're receiving now left TON 618 when the universe was less than a quarter of its current age. We're seeing this monster as it existed in the ancient past, when galaxies were younger, when the universe was more chaotic, when ultramassive black holes like this were perhaps more common than they are today. The observation problem and hidden giants. But here's the thing about TON 618 that should make you pause. We're seeing it as it was 10 billion years ago. Light takes time to travel. When we observe distant objects, we're looking back in time. TON 618 is so far away that the light we're receiving now began its journey toward Earth 10 billion years ago. And in those 10 billion years, that black hole has almost certainly continued growing. How much bigger is it now? We have no way of knowing. We can't see TON 618 as it exists today. We can only see its ancient past. For all we know, it might have doubled in size. It might have merged with other ultramassive black holes. It might have consumed entire galaxy clusters worth of matter. Or maybe its food supply ran out and it's been sitting there quietly for billions of years, barely growing at all. This is one of the fundamental challenges of astronomy. We're not seeing the universe as it is. We're seeing the universe as it was. The further away something is, the further back in time we're looking. And that means our census of ultramassive black holes is inherently incomplete. The largest black hole in the observable universe might be something we haven't even detected yet. Sitting in a distant galaxy whose light hasn't reached us. Or it might be TON 618, grown even larger in the billions of years since the light we're seeing left it. There might be black holes out there with 100 billion solar masses. Or 200 billion, or more. We simply don't know. And unless we develop faster than light travel, or find some way to observe the universe in real time, rather than looking at ancient light, we'll never know for certain what the current record holder is. The ultimate fate and cosmic perspective. Ultramassive black holes, like Ton 618, will be among the last objects to exist in our universe. Long after the last stars burn out, long after galaxies disperse and fade, black holes will remain, and they'll continue growing, albeit slowly, by capturing dark matter and the occasional stray object. Eventually, over timescales so vast, they make billions of years seem like seconds. Even black holes will evaporate through Hawking radiation. But the ultramassive ones will be the last to go, persisting for googles of years. So in a sense, we're living in a universe where ultramassive black holes are still young. They're still growing. They're still active. Billions of trillions of years from now, when the cosmos has grown cold and dark, these objects will still be there, slowly radiating away their mass. The final remnants of a universe that once blazed with light and energy. And that brings us full circle to where we started. From primordial black holes, smaller than atoms, formed in the first fraction of a second after the Big Bang, to ultramassive giants containing billions of solar masses. From theoretical entities we've never observed to photographed monsters dominating galactic centers. From objects that might be dark matter to objects that shine brighter than 100 trillion stars. Black holes represent the extremes of physics, the places where our theories are pushed to their absolute limits. They're nature's ultimate demonstration of what happens when you concentrate matter and energy into the smallest possible space. They're laboratories for testing general relativity in its most extreme regime. They're time machines that let us look back to the universe's youth. They're the engines driving cosmic evolution, regulating galaxies, triggering star formation, creating the heavy elements necessary for life. We've journeyed from the smallest to the largest, from the theoretical to the observed, from the calm to the violent. And every step of the way, black holes have challenged our understanding, exceeded our expectations, and reminded us that the universe is far stranger and far more extreme than we ever imagined. These cosmic monsters will outlive everything else, growing ever larger, ever more dominant, until finally, in the unimaginably distant future, they too fade away into quantum foam and radiation. That's the story of black holes. From quantum specks to ultramassive titans, from mathematical curiosities to photographed reality, from the universe's beginning to its ultimate end. And we're privileged to live in the brief cosmic moment when we can observe them, study them, and try to understand what they tell us about the fundamental nature of existence itself. And so, as these giants drift through the ages, outlasting stars, galaxies, and the universe itself, we stand here in the brief moment when we can still see them, still learn from them, still marvel at what they reveal. Black holes are the universe at its most extreme, yet they illuminate its deepest truths. Tonight, we leave them not as monsters, but as quiet reminders of how vast, beautiful, and mysterious existence truly is. Sleep well, and every night we get one step closer to uncovering the universe's deepest mysteries. Don't forget to subscribe so you never miss a new episode. Thank you in advance, and good night.